A Brief History of Time, written by Stephen Hawking, is one of the most celebrated books in science. It invites readers into the mysterious depths of the universe, exploring time, space, black holes, and even the origin of everything we see. Hawking reveals the secrets of physics in a way that anyone can understand, yet every page raises new, mind-bending questions. What is the universe really like? How does it begin and could it ever end? What is time and could it ever stop? Could we travel back into the past, or are we forever bound to move forward? The mysteries of the cosmos are older than any one mind, and history is filled with strange ideas that once challenged accepted truths. A famous scientist, often thought to be Bertrand Russell, once gave a lecture on astronomy, explaining how the Earth revolves around the Sun and how the Sun sits at the center of a vast galaxy. Afterward, an elderly woman stood up and said everything he had explained was wrong. According to her, the Earth was like a massive plate resting on the back of a colossal turtle. The scientist laughed and asked, "What does the turtle stand on?" The woman replied simply, "You are clever, but there is only a turtle beneath." Most people would dismiss this as a joke. Yet it forces us to ask a deeper question. How much do we truly know about the universe? What we believe today may be overturned tomorrow. Just as humanity once thought the Earth was flat, and Aristotle in 340 BC wrote in On the Heavens that the Earth was immovable and not round, the truths we cling to may later appear as naive or even absurd. The universe is far stranger than our minds can imagine, yet science continues to uncover its secrets. Theories like relativity and quantum mechanics hint at a reality far beyond common perception, revealing a universe that is alive with mystery, wonder, and infinite possibility. Hawking's genius lies not only in answering questions but in showing us the vast unknown. Every black hole, every particle, every twist of time and space opens doors to more questions. Are we truly at the beginning, or somewhere in an endless cycle? Could time itself bend, stretch, or even loop back on itself? As we turn the pages, curiosity grows, and the universe becomes a puzzle more fascinating and terrifying than any story ever told. The story of the cosmos is not just for scientists. It is a challenge to every human mind. Every discovery sparks wonder, and every answer invites new questions. By the end of this book, we are left in awe, realizing how small we are, yet how limitless the pursuit of knowledge can be. He had two major pieces of evidence. First, when the Earth comes between the Sun and the Moon during a lunar eclipse, the shadow that falls on the Moon is always round. If the Earth were flat, the shadow would sometimes look like an ellipse or an elongated egg. Secondly, when the Greeks traveled south, the North Star would be seen downward. From the North Pole, it would be seen straight up, but from the equator, it would be near the equator. From these differences, Aristotle estimated the size of the Earth to be 400,000 stadia. This was almost double the actual size today. A third piece of evidence was that when a ship came from afar, its sails would first be visible. Then gradually, the entire ship would become visible. Aristotle believed that the Earth was stationary, and that the Sun, Moon, and planets revolved around it. Ptolemy developed this model further in the 2nd century. His model had the Earth at the center, and 8 spheres around which the Moon, Sun, stars, Mercury, Venus, Mars, Jupiter, and Saturn revolved. The stars were attached to a fixed sphere that rotated. This model was accurate, but there was a problem. This model had to accept that the Moon sometimes came close to the Earth and sometimes went far away, which was not visible. Yet the Christian Church accepted this model as divine, because it had room for heaven and hell. In 1504, Nicholas Copernicus gave a new model. In it, the Sun was at the center and the planets revolved around it. This model was first circulated secretly, because the Church would have considered it heresy. In 1609, Galileo saw through a telescope that small moons revolved around Jupiter. This meant that everything did not revolve around the Earth. Johannes Kepler changed Copernicus's circular orbit to say that the planets had elliptical or oval orbits. This theory began to match accurate observations. In 1687, Isaac Newton published Principia Mathematica, which is considered the greatest book of the Church. In it, Newton gave the laws of motion and space-time. He gave the law of universal gravitation, that every object attracts every other object. The bigger it is and the closer it is. This was the force that pulled the object down toward the Earth. The famous story of the apple falling gave Newton the idea of gravity. Maybe it was just a story. Newton showed that gravity causes the Moon to revolve around the Earth and the planets to orbit the Sun. After the Copernicus model, the idea of a cosmic sphere ended. Now it was accepted that the stars were like the sun but very far away. But Newton found a big problem. If the universe was infinite and stable, then there should be some star in each direction. This means that the entire sky of Nupur should look as bright as the sun. Newton wrote a letter in 191 where he said that if the stars were finite, they would tend towards each other. But if they were infinite, they would tend towards infinity. This was a problem of infinity. Now we know that a stable infinite universe is not possible. If gravity were to attract, then the universe would either expand or contract. Before the 20th century, people believed that the universe had either always been the same or that God had created it all at once. Newton's law of gravity showed that the universe could not be stable. But people ignored this and tried to change gravity so that a balance would be maintained. They thought of gravity as repelling or pushing far enough apart so that the stars would be in balance. But now we know that if this model existed, the universe would be unstable. If some stars were to come closer to each other, they would come closer. And if they were to go further away, they would have gone further. Before the 20th century, no one thought that the universe could expand or contract. Everyone thought that the universe had always been like that. But now we know that the universe is expanding. Evidence for this comes from Einstein's theory of relativity and Edwin Hubble's discovery that galaxies are moving away from each other. If this is true, it means that at some point the universe was in a smaller place. This means that the universe had a beginning, which we now know as the Big Bang Theory. Another major objection to an infinite and stable universe was made in 1823 by the German philosopher Heinrich Olbers. Scientists in Newton's time had also thought about this, but Olbers' argument is the most famous. The problem was that if the universe were infinite and stable, there should be stars in every direction. This means that the entire sky at night should look as bright as the sun. Olbers replied that the light from distant stars was absorbed by the dust and gas in between. But if that were the case, then that matter would have gradually heated up and become as bright as stars. There was only one solution to this problem. Either the stars had a finite beginning or their light had not yet reached us. This raises the big question of when these stars began. The question of the beginning of the universe was discussed by ancient civilizations and the Judeo-Christian and Muslim traditions that it had a finite beginning. One argument was that everything happens for a reason. Therefore, the universe must have had a first cause. The Christian thinker St. Augustine wrote in his book, The City of God, that human civilization was progressing. If we can remember the discoveries of civilization or important people, then this means that human civilization cannot be very old. St. Augustine, based on Genesis, believed that the universe was created in 5000 BC. This assumption is surprising, because according to archaeologists, civilization began around 10,000 BC. Greek philosophers like Aristotle did not like the theory of creation, because it seemed like divine intervention. They believed that mankind and the universe had always been and always will be. In response to St. Augustine's argument for progress, they said that repeated major disasters, such as floods or disasters, set civilization back to the beginning. Philosopher Immanuel Kant discussed the beginning of the universe in depth in his book Critique of Pure Reason in 1781. He called it an antinomy. This means a contradiction where there is a strong argument on both sides. On one side was the argument that if the universe did not begin, then there would have been an infinite amount of time before any event, which seems inconsistent. On the other side was the argument that if the universe began at a specific time, then there would have been an infinite amount of time before it. So why did the universe begin at a specific time? The basis of both arguments was the same. It is believed that time can go back to infinity. But St. Augustine had already said that time has meaning only when the universe exists. When he was asked what God was doing before he created the universe, his answer was that time itself was something that God created with the universe. Before the universe, time had no meaning. Previously, people believed that the universe had always been the same. For this reason, the question of its beginning was considered a matter of philosophy or theology. You could say that the universe has always existed, or you could say that God began the universe at a certain time in such a way that it looked old. But in 1929, Edwin Hubble made a big discovery. Galaxies are moving away from us. This means that the universe is expanding. This means that it was closer before, and if you go back, there was a time when the universe was in one place and its density was infinite. This formed the basis of the Big Bang Theory. For the first time, the question of the beginning of the universe became a scientific topic. Hubble's discovery showed that at some point the universe was infinitely small and infinitely dense. In such a situation, all the laws of physics would have become invalid. If any events had occurred before the Big Bang, they would have had no effect on the universe today. This means that there was no definition of time before the Big Bang. This means that time began with the Big Bang. Earlier, people used to think of a stable universe. For this reason, they believed that the universe had a creator or origin from an external force. But if the universe is expanding, then perhaps there was a supernatural reason for its beginning. Some may say that God began the universe at or after the Big Bang, but imagining a universe before the Big Bang is pointless. If we want to understand the nature of the universe and want to know whether it had a beginning, we first need to understand what scientific theory is. A theory is a model that explains some part of the universe. If it matches observations and makes new predictions, then it is a good theory. For example, Aristotle believed that everything is made of 4 basic elements: earth, air, fire, and water. But it made no predictions. Newton's law of gravity was both simple and made predictions with high reliability. In science, no theory is definitively proven. A theory survives until an experiment proves it wrong. For example, Newton's law of gravity slightly incorrectly predicted the motion of the planet Mercury. Einstein's theory of relativity, the theory of relativity corrected that. But Newton's laws still work in everyday use today because they are simpler and rely on smaller scales than Einstein's relativity. The ultimate goal of science is to create a theory, a single theory, that describes the entire universe. Scientists look at 2 things separately: the laws that can tell how the universe is changing, and what the universe was like in the beginning. If a final theory can be found that can explain time, space, gravity, quantum mechanics, and the origin of the universe together, it will be the greatest discovery of science. Some people believe that science will only focus on the laws of the universe. But the question of its beginning is a matter of religion or metaphysics. They say that God is all-powerful, so he could have started the universe in any way. If that were the case, then the development of the universe could have been completely random. But that is not the case. The universe has evolved in a certain way according to certain rules. If the rules apply to the evolution of the universe, then it is logical that some rules should also apply to its initial state. It is quite difficult to create a theory to explain an entire universe. So we create different partial theories. Each theory explains only a limited set of observations. It ignores other factors or presents them only in simple numbers. This approach may be wrong. If every element of the universe is deeply dependent on each other, then it is impossible to arrive at a complete solution by studying each part separately. But this is the only way we have made progress so far. Newton's theory of gravity is the best example of this. Newton showed that the gravitational force between 2 objects depends only on their masses. This means that we do not need to understand the gravitational attraction of the sun and the planets. If we know only their masses, we can calculate their motions. Today we describe the universe with 2 large partial theories. First, the general theory of relativity, and second, quantum mechanics. The general theory of relativity explains gravity and the large-scale structure of the universe. This theory includes scales from a mile to a trillion miles, i.e., 24 zeros after 1. Quantum mechanics describes phenomena on very small scales, which are equal to a millionth of an inch. But there is a big problem. These 2 theories do not match each other. Relativity describes gravity. Quantum mechanics works at the microscopic level. But both cannot work together. That is, both cannot be correct. Today, one of the biggest discoveries in physics is underway, the quantum theory of gravity, a theory that will combine both relativity and quantum mechanics. We do not have this theory now, and it may take a long time to get it. But we already have an idea of some important features of this theory. In the following chapters, we will see how we already know some of the predictions of quantum gravity theory. If you believe that the universe follows certain rules, then eventually all the partial theories will be combined into a final theory that will describe the entire universe. But there is a big discrepancy here. We believe that we are rational beings who can independently observe the universe and make logical conclusions. If a fully unified theory exists, then it will also determine our actions. That is, that theory will determine whether we can reach the right conclusions or not. Then the big question arises, will that theory force us to reach the wrong conclusions, or will we not be able to reach any conclusions at all? Darwin gave an answer to this discrepancy in the principle of natural selection. The organism that can correctly understand the world around it and react accordingly survives. The organism that reaches the wrong conclusions goes extinct. To this day, intelligence and scientific discovery have helped to survive. But today, it is not clear whether science will always help us survive. Our discoveries can also destroy us, and even if we find a complete theory, it may not affect our survival. Science has already provided quite reliable theories, which can explain everything except the most extreme situations. This means that in practical life, we will be able to do without a final theory. But if we had applied this logic in the past, quantum mechanics and the theory of relativity would never have come, and they gave rise to breakthrough discoveries such as nuclear power and microelectronics. A final theory may not help us survive, but we will continue to strive for it. Why? Because since the beginning of civilization, people have not wanted to see events randomly. The greatest goal of our curiosity is a complete description of the universe. Why are we here? Where did we come from? These questions are the most complete and profound questions of mankind. And until they are answered, we will keep searching. Time and space. The laws of motion that we know today come from Galileo and Newton. Before that, people followed Aristotle. Aristotle said that any object is at rest in its natural state and moves only when it is acted upon by a force. This meant that heavier objects would fall faster than lighter objects because they would be more attracted to them. Aristotle and his followers believed that thinking this way would explain the laws of the universe without the need for experiments. No one had ever tried to test whether objects of different weights actually fell at different speeds. They thought it was pure thinking. Then Galileo tested Aristotle's idea. There is a story that Galileo tested by dropping objects from the Leaning Tower of Pisa. But this is not true. Galileo Musrin rolled balls of different weights down a slope. It showed the same gravitational effect, but it would increase in speed gradually. This made it easier to measure. The result was that the weight of an object did not affect its acceleration. If a slope went down 1 meter every 10 meters, a ball would increase in speed by 1 meter per second after 1 second, by 2 seconds, by 2 meters per second, and so on, whether it was a light ball or a heavy one. A feather and a heavy weight fall differently in air because the air resistance was different, but if there is no air resistance, both will fall together. Apollo 15 astronaut David R. Scott tested this on the moon. There is no air on the moon, so both the feather and the heavy weight fell together. Galileo used Newton's experiments to develop Newton's laws of motion. Galileo showed that as long as an object is rolling down a slope, the force, or gravity, accelerates it every second. Newton proved that the real function of force is to change the motion of an object, not just to move it. Newton wrote the Principia Mathematica in 1687, where he gave the laws of motion and gravity. Newton's first law was that if no force is applied to an object, it will always move at a constant speed in a straight line. Newton's second law was that when a force is applied to an object, it accelerates it. Acceleration is proportional to the force and inversely proportional to the mass. That is, the more force, the greater the acceleration. The more mass, the less the acceleration. The more powerful the engine of a car, the faster it will accelerate. But the heavier the car, the less the acceleration. Newton showed that every object attracts every other object, and the force is proportional to the mass. If the mass of one object doubles, the gravitational force also doubles. If the mass of one object doubles and the mass of the other triples, the force will be 6 times. This is because all objects fall at the same speed. A heavier object will take twice the force, but its mass will also double. According to Newton's second law, the force and mass will cancel out, and the acceleration will remain the same. Newton also said that the greater the distance, the less the gravity. If the gravitational force of a star quadruples, then the square of the distance will become 1 to 4. If the law of gravity were different, the planets would not be able to move in elliptical orbits. They would either fall into the sun or move out. According to Aristotle, there was a certain state of stability. He believed that the Earth was stationary and everything else was rotating. Newton showed that there was no such thing. There is no point of absolute stability. If a train is moving at 90 miles per hour, we can say that the train is moving and the Earth is stationary, or the Earth is moving and the train is stationary. If someone on the train plays ping pong balls, the ball will move as it moves on the table on the track, i.e., speed is relative, not absolute. If speed is not absolute, then there can be no absolute position of any event. For example, a ball inside the train will be seen falling straight down, but a person standing on the track will see the ball falling in a circle because the train is moving. This means that the position of any event can be different for different observers. Newton was worried about this, because it was inconsistent with his idea of an absolute God. But philosophers accepted this idea. Newton and Aristotle believed that time was absolute. Any observer would get the same result if they measured time. Time and space are separate. This seemed common sense, but it was wrong. In 1676, Danish astronomer Ole Rimmer showed that light travels at a fixed speed. The moons of Jupiter do not always orbit at the same distance. As the distance between Earth and Jupiter increases, light is delayed. Rimmer estimated the speed of light at 140,000 miles per second. This is close to the modern standard of 186,000 miles per second. In 1865, James Clerk Maxwell developed the theory of electromagnetic radiation. He said that light is a wave that travels at a fixed speed. If the wavelength is long, radio waves are produced. If the wavelength is short, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are produced. Newtonian physics correctly predicts the motion of apples, cars, and planets. But when the speed approaches the speed of light, Newtonian physics fails. This is where Einstein's theory of relativity begins. Maxwell's theory predicted that radio and light waves travel at a fixed speed, but Newton had abandoned the idea of absolute stability. If the speed of light was constant, the question arose as to what this speed would be measured against. To solve this problem, a hypothetical substance called ether was proposed. It was assumed that light waves travel in the ether, just as sound waves travel in air. If the ether existed, observers would see a serpent of the ether. They thought that the speed of light should be different for them. That is, when the Earth was moving towards the ether in its orbit, the speed of light should be faster. And when the Earth was moving perpendicular to the ether, the speed of light should be slower. In 1887, Albert Michelson and Edward Morley did a very careful experiment at the Cleveland School of Applied Science. They measured the speed of light in the direction of the Earth's motion and perpendicular to it. The result was that the speed of light was the same in both directions. This was unexpected because if there was an ether, the speed should be different. In 1887, George Fisher and Heinrich Lorentz came up with a solution that moving objects contract and clocks run slower. But these explanations seemed artificial. In 1905, Albert Einstein, who was then a clerk in a Swiss patent office, published a paper. He said that the ether was not needed and that we only had to give up the idea of absolute time. Henri Poincaré also said the same thing, but Einstein's method was based on physics. That's why he is credited with the theory of relativity. Einstein's theory of relativity had two major consequences. First, the relationship between energy and mass, equal to mc squared, and the end of the concept of absolute time. Einstein showed that mass and energy are related to each other. According to equal to mc squared, as speed increases, energy increases, and mass also increases. For example, if an object moves at 10% of the speed of light, its mass increases by only 0.5%. If it moves at 90%, its mass will double. If an object starts approaching the speed of light, its mass will become infinite. So only light or massless waves can travel at the speed of light. Secondly, they ended the concept of absolute time. In Newtonian physics, time was an absolute quantity, meaning it was the same for everyone. If an observer sees a pulse of light traveling from one place to another, all observers will agree on how long it took, but not all will agree on how far it traveled. In relativity, the opposite is true. All observers will agree that the speed of light is the same, but they will not agree on how far the light traveled. If the distance is measured differently, then time will also be measured differently. This means that each observer will have their own different time scale. If two observers carry identical clocks with them, they will certainly disagree. Each observer can send a radar pulse to measure their time and position. The observer sends the pulse, which is reflected from an object, and the observer receives the reflection. The time of that event is the time between sending the pulse and receiving the reflection. The position of the object can be found by multiplying the speed of light. This process is shown in relativity by the space-time diagram. If two observers move relative to each other, they will measure the same event at different times and positions. No observer's measurement is right or wrong, but all observers' measurements are linked by an equation. Today we use time to measure distance accurately. A meter is defined as the distance that light travels in 0.3305 64095 330 feet 64095 of a second. This number was chosen because it matches the historical meter definition of the Platinum Bar in Paris. In the theory of relativity, distance is defined in terms of time and the speed of light. Therefore, each observer will always see the speed of light the same. The Michelson-Morley experiment showed that the ether does not exist. The theory of relativity says that the ether is not needed. In one physics, space and time were completely separate things. 3 coordinates were needed to describe the position of an object. Time was an independent quantity. But Einstein's theory of relativity showed that space and time are not separate but the same thing, space-time. To define an event, we need 4 coordinates. 3 coordinates of space and 1 of time. If light comes out of one place, it will create a 3-dimensional angle in space-time that will go forward into the future. This angle is called the angle of future light. Similarly, past events also have an angle where those events are located from which light can come out to reach a particular event. This angle is called the angle of past light. For a particular event, P, all events in the universe can be divided into 3 parts. The angle of future light is the angle of past light and elsewhere. The angle of future light is those events that will happen after P, and where light can reach it at or below the speed of light. The angle of past light means those events that can affect P because the light or signal emitted from those events can reach P, and elsewhere means those events that cannot reach P because they have to travel faster than the speed of light. For example, current events on the Sun will be in the same category as current events on Earth. This is because it takes about 8 minutes for sunlight to reach Earth. After 8 minutes, Earth will be at the future light angle and will feel the effects. Similarly, when we look at a distant galaxy, we are not looking at its current state, but at its past state millions or billions of years ago. In 1905, Einstein proposed the special theory of relativity, which ignored gravitational effects. There would be a light angle for every event. This is because the speed of light was the same everywhere. Therefore, every light angle pointed in the same direction. The theory of relativity states that nothing can move faster than the speed of light. If an object moves, its path will always be within the angle of the light. If Newtonian gravity were correct, it would mean that the gravitational force exerts a strong influence, which is incompatible with relativity. Between 1908 and 1914, Einstein tried many times to create a theory of gravity that was compatible with relativity. In 1915, Einstein finally proposed a revolutionary theory called the general theory of relativity. Einstein said that gravity is not a force but a result of the curvature of space-time. Newton believed that objects attract each other with a force. Einstein said that objects move in a curved space-time where they follow a naturally geodesic, i.e., straight path. For example, consider the Earth revolving around the Sun without any force but following a natural geodesic in a curved space-time. For example, if an airplane flies on a round Earth, it will follow the shortest path, i.e., a great circle. Similarly, planets follow curved paths in space-time. Newtonian gravity correctly predicted the elliptical orbits of planets. But Mercury's orbit behaves somewhat differently. Einstein's general relativity predicted that Mercury's orbit would slowly process, i.e., rotate around the axis of the ellipse. This could not be explained by Newtonian physics. But Einstein's theory made the correct predictions. Later, small deviations of other planets were also examined by radar surveys and were consistent with general relativity. Another major prediction of general relativity was that gravity would bend the path of light. If a star's light passes by the Sun, it would bend slightly and make the star appear to shift in position to us. This is impossible to see on a normal day because sunlight blocks out stars. But in 1919, a British expedition proved during a solar eclipse that light does indeed bend. It was a major moment when the German theory was proven by British scientists. It became a symbol of peace after the First World War. General relativity predicts that time slows down near gravity. The stronger the gravity, the slower time will run. If a ray of light travels up against gravity, it will lose energy and its frequency will decrease. In 1962, an experiment was conducted in which accurate clocks were placed at the top and bottom of a tall water tower. The clocks at the bottom, which were in higher gravity, ran slower. This was exactly as predicted by general relativity. Today, GPS satellites take this effect into account. Otherwise, the position calculation could be off by kilometers. In Newtonian physics, time was absolute, but in relativity, time is relative. Suppose one twin lives on a mountain and the other on the ocean floor. When the two meet, the twin on the mountain will be a little older because his time was running faster. If a twin travels through space at close to the speed of light, his brother will be much older than him when he returns. This twin is confused only when someone thinks that absolute time is real. According to relativity, each person's time can be different. depending on his speed and location. Before 1915, space and time were considered a fixed phase in which events occurred. In Newtonian physics, forces only affected objects, but space and time remained unchanged. In general, special relativity also had a fixed background. But general relativity showed that space and time are also dynamic. They are also affected by events occurring in the universe. When an object moves or acts on a force, the curvature of space-time changes. Space and time are not just backgrounds, but are actively involved in the motion of the universe. After general relativity, the idea of a static universe ends. The universe becomes a dynamic entity, which will either expand or contract. The old idea that the universe had always been the same was proven wrong. In the following chapters, we will see how this discovery revolutionized the Big Bang theory. This new concept of space-time was the basis for the work of Roger Penrose and Stephen Hawking, who showed that the universe could have a definite beginning and perhaps a definite end. The expanding universe. If you look at the sky on a clear, dark night, the brightest objects you can see are the planets, such as Venus, Mars, Jupiter, and Saturn. There are thousands of stars in the sky that are like our sun, only much farther away. Many people think of stars as stationary, but they actually move a little. As the Earth revolves around the sun, we see these stars from different positions. This movement is very small, only for stars that are close to us. The nearest star, Proxima Centauri, is 4 light-years away. That means its light takes 4 years to reach us. That's the equivalent of 23 trillion miles. The stars that we can see with the naked eye are within a few hundred light-years. Our sun is only 8 light-years away. The stars that we see in the night sky seem to be spread out all over the place, but they are very dense in one place. This band or region is called the Milky Way. In the 1750s, some astronomers proposed that the Milky Way might be like a disk. Then William Hussell listed the positions and distances of many stars, which confirmed that we were in a spiral galaxy. Until 1924, people thought that this was the entire universe, but Hubble proved that there were more galaxies. Hubble showed that there were thousands of galaxies besides our own. But to prove this, he had to measure the distances to the galaxies. We can measure the distances to nearby stars directly, but galaxies are very far away. That's why Hubble used an indirect method. The brightness of a star depends on 2 things. Its true brightness is called luminosity and its distance. If we know the true brightness of a particular type of star, we can measure its apparent brightness and find out its distance. If the distances to different stars in the same galaxy are the same, then we can be sure that we have made the right measurement. This is how Hubble was able to find out the distances to 9 galaxies. Today we know that our galaxy is one of 100 billion galaxies that we can see with modern telescopes. Each galaxy contains up to 100 billion stars. We live in a spiral galaxy that is 100,000 light-years wide and is rotating slowly. The stars in the galaxy take hundreds of millions of years to orbit the center once. Our sun is an average yellow star located near the inner edge of the spiral arms. We can understand how far we have come. In the past, people thought that the Earth was the center of the universe. Stars are very far away, so they only appear as bright points. We cannot know their size or shape. The most important way to identify a star is by the color of its light. Newton showed that if light passes through a prism, it splits into different colors. Similarly, if we look at the light of a star through a telescope, we can see its spectrum. Different stars have different spectra. A bright object emits a specific thermal spectrum. Certain colors are absent from the spectrum. Each chemical element absorbs a unique set of colors. If this blue is seen in the spectrum of a star, we can tell its elements. In the 1920s, when the spectra of stars in other galaxies were observed, a strange thing was found in them. Their spectra were shifted to the red. This is due to the Doppler effect. When an object comes towards us, the wavelength of its light becomes shorter. That is, it is blue shifted. When an object moves away from us, its wavelength becomes longer. That is, it is red shifted. For example, the sound of a car is heard with high pitch when the car is approaching and with low pitch when it is moving away. Similarly, light shifts with the medium sources. Hubble listed the galaxies by distance and their redshift. If the galaxies were rotating randomly, some blue shifted and some red shifted. But almost all the galaxies showed red shifted. That is, they were moving away from us. In 1929, Hubble made another big discovery. The farther away galaxies are, the faster they are moving away from us. This meant that the universe is not static, it is expanding. Newton and the physicists who followed him should have understood that if the universe were static, gravity would compress it. If the universe were expanding slowly, gravity would pull it back in. If the universe were expanding faster than a certain speed, gravity would never stop it. It would always keep expanding. This is the same idea that applies to the speed of a rocket. If a rocket were moving slower, gravity would pull it back in. If it were going faster than 7 miles per second, it would run away and never come back. This could have been predicted long ago from Newtonian physics. But people believed in a static universe so strongly that no one thought about it. Even Einstein thought a static universe was true when he developed general relativity. He added an artificial cosmological constant that worked against gravity. This force did not come from any object but existed within the fabric of space-time. It was designed to keep the universe in balance. But after Hubble's discovery, Einstein admitted that this was his biggest mistake. Only one person took relativity seriously. He was the Russian physicist Alexander Friedmann. Einstein and other physicists were looking for a solution to a static universe. But Friedmann was trying to understand an expanding universe. Alexander Friedmann made 2 general assumptions about the structure of the universe. First, the universe looks the same in every direction. And second, this assumption would be valid if viewed from any other place. Based on these 2 assumptions alone, Friedmann showed that the universe cannot be static. That is, it will either expand or contract. Friedmann made this decision in 1922. Hubble observed it in 1929, a few years before Hubble's discovery. Friedmann had predicted it. On a practical level, the universe is not written the same everywhere. The Milky Way looks like a band. Galaxies are in clusters. They are not evenly spread out everywhere. But when we look at large scales, galaxies seem to be evenly spread out in all directions. People had previously thought Friedmann's guess was a rough approximation. But in 1965, scientists Arno Penzias and Robert Wilson at Bell Telephone Laboratories were testing a sensitive microwave detector. The detector was picking up an unwanted noise. They checked all possible sources, instrument malfunctions, the atmosphere, bird poison, everything. The noise was the same everywhere and was constant day and night throughout the year. This meant that this noise was not coming from the solar system, but from the entire universe. It later became known as the cosmic microwave background radiation. It was a leftover signature of the Big Bang. At that time, Bob Dickey and Gene Publiso at Princeton University were interested in microwaves. They were researching the ideas of Friedmann's student George Gamow. Gamow had said that the early universe was very hot and dense. It emitted white-hot radiation. If this galaxy had ever existed, it would be visible today in the form of extremely redshifted microwave radiation. While Beck and Peebles were planning to look for it, Penzias and Wilson learned about their work and realized that they had already discovered it. Penzias and Wilson won the Nobel Prize in 1978, but D.K. Peebles and Gamow did not. That seemed a bit unfair. If galaxies were moving away from us in every direction, one might think that we were at the center of the universe. But Friedmann's second hypothesis was that it would look the same from every location. If there were spots on a balloon, when the balloon was inflated, all the spots would move away from each other. When viewed from each spot, all the other spots would appear to be moving away. But there is no center. Friedmann's model matched Hubble's observations of redshift exactly. But his work remained unknown in the West until Howard Robertson and Arthur Walker reproduced the same model in 1935. Friedmann's equations gave rise to 3 possible models of the universe. First, a closed universe that would expand and contract. If the expansion were slow, gravity would pull it back together and contract again. After a while, all the galaxies would come together. This could be a cyclical model, a big bang followed by a big crunch. Second, an open universe that would always expand. If the expansion were very fast, gravity would not be able to stop it. The galaxies would always move away from each other. The universe would expand infinitely. Third, a critical universe that is in equilibrium. The expansion is so fast that gravity is keeping it in equilibrium. The expansion will slow down but never stop. To determine this, we need to measure the current expansion rate and density of the universe. We can accurately measure the speed of galaxies from the Doppler effect. We know that the universe is expanding by 5 to 10% every billion years, but it is difficult to accurately measure the exact distance between galaxies. If we add up the mass of all the visible galaxies, it is too small to stop the expansion. But galaxies contain dark matter, which is not directly visible, but has an effect on gravity. Even if we add dark matter, the total mass is only 1/10 of the mass needed to stop the expansion. There is no evidence yet that there is any other hidden matter that can contract the universe. This means that the universe will probably always be expanding. But if there is any extra matter, it could contract at some point in the future. Friedman's model says that at a certain point in time, galaxies were in the same place. This was a singularity, or the Big Bang. There, the density and curvature were infinite. Mathematics cannot handle infinite numbers. This is why the equations of relativity fail here. If there were any events before the Big Bang, they would not have affected the future. That means the Big Bang is the beginning of time for science. Some scientists were associating the Big Bang with the idea of divine creation, which was not acceptable to them. In 1948, Herman Bundy, Thomas Gould, and Fred Hoyle proposed the steady-state theory. They said that the universe appears to be stable because new galaxies are constantly being formed. When a galaxy moves away, a new star system is formed in its place. That means the universe will always look the same. This theory predicted that there should be the same number of galaxies in any part of the universe at any time. In the 1950s, radio surveys by Cambridge astronomer Martin Ryle proved that there were more galaxies in the past. If there were more galaxies in the past, then the universe could not be stable. Penzias and Wilson's discovery of microwave radiation was evidence that the universe was very dense in the past. In 1965, the steady-state theory was officially rejected. The Big Bang had become a scientific fact. But now the question is, how did the universe evolve after the Big Bang? Another attempt to avoid the Big Bang was made in 1963 by two Russian scientists, A. Janis Lifshitz and Isaac Latnik. They said that the Big Bang might be just a limitation of Friedman's model, which is a rough guess. In the real universe, galaxies are not just moving away in a straight line, but are also moving sideways. If sideways motion is taken into account, then maybe the universe it didn't collapse. Maybe the universe was in a collapsed state where particles didn't come together and passed each other. And now it's expanding. Lifshitz and Latnikov created a model where galaxies were moving at random speeds. They showed that in some special cases the universe could start from a singularity, but they said that such special models would be very rare. In most cases, the Big Bang singularity didn't exist, but in 1970 they retracted this claim, because it turned out that many models had singularities. Lifshitz and Latnikov's work couldn't prove that the Big Bang should have happened according to general relativity. The answer came from a new method that Roger Penrose gave in 1965. Penrose showed that when a star collapses under its own gravity, it gets stuck in a region that can have zero size. That is, all its mass becomes an infinitesimal point, a singularity. This singularity resides inside a black hole. At first it seemed to apply only to stars, not to the entire universe. But at that time, Stephen Hawking was looking for a problem for his PhD. Hawking was diagnosed with ALS, or motor neuron disease, in 1963, and the doctors said he would live for a year or two. For this reason, he initially did not focus on a PhD. But when he survived, he thought about continuing his research. He read Roger Penrose's theorem and realized that if time is reversed, it also applies to the Big Bang. If the contraction in Penrose's theorem is reversed, then an expanding universe should also start from a singularity. Penrose's theorem said that a contraction would be infinite. Hawking showed that an expanding universe would start from a singularity. This is possible only if the universe behaves like Friedman's model on large scales. At first, Penrose's theorem only applied to cases where the universe was infinite. Hawking developed new mathematical techniques that could overcome this limitation. He proved that if general relativity is correct and there is as much matter in the universe as we can see, then there must be a singularity. In 1970, Hawking and Penrose published a joint paper in which they proved that according to general relativity, the universe must have started from a singularity, from a Big Bang. This meant that time and space had a definite beginning. General relativity is an incomplete theory because it cannot say how the universe began. If at some point all physics fails, we cannot say anything about the past. Hawking and Penrose's work was much criticized in Russia. Communist scientists believed in determinism, and the singularity meant that the universe was unpredictable, which was against their ideals. Some scientists didn't like it either, because Einstein's universe was an elegant and rational theory, and the singularity made that theory look strange. But there is no argument against a mathematical theorem. In the end, everyone accepted it. To this day, most scientists believe that the universe began with a singularity. Hawking proved this theorem, but today he believes that maybe the singularity wasn't real. Adding the effects of quantum mechanics can avoid the singularity. In just 50 years, the entire cosmological perspective of human history has changed. Hubble's discovery showed that the universe is expanding. We realize that space-time is dynamic. As research continued, it became increasingly clear that the universe had a definite beginning. In 1970, Hawking and Penrose finally proved that according to general relativity, there must have been a Big Bang singularity. But general relativity is a partial theory. It cannot say what happens inside the singularity. A new theory is needed to get beyond the point where physics breaks down. If there was a Big Bang singularity, it was in a region where quantum effects were dominant. Relativity works on large scales. Quantum mechanics works on small scales. But when the universe was very small, both effects were important. In the early 1970s, physicists realized that relativity alone could not provide the answer. Now the focus has shifted to a new goal, the quantum theory of gravity. In the following chapters, we will see what quantum mechanics is, how it relates to gravity, and what a complete theory that can explain the beginning and evolution of the universe would look like. What would that look like? The uncertainty principle. In the 1900s, seeing the success of Newton's theory of gravity, the French scientist Marquis de Laplace gave an idea that if we knew the exact state of the universe at some point in time, we could predict the future. That is, a deterministic universe where everything goes according to a certain law. If we knew the position and motion of the planets, we could calculate their motion forever using Newton's laws. Laplace said that this law was not limited to planets but applied to everything. Even in human behavior, this idea of scientific determinism was not liked by many people, because there was no room for God to intervene in it. But this law, the belief persisted until the early 20th century, until quantum physics broke it. The first challenge to the determinism of Newtonian physics came in the late 19th century. Lord Rayleigh and Sir James Jeans showed that if a hot object radiated heat, it should radiate the same amount of energy at every frequency. The problem was that if the same amount of energy was emitted at every frequency, the total energy would be infinite. This was physically impossible. Max Planck came up with a solution in 1900. Light and energy waves are not emitted continuously, but in small packets called quanta. The higher the frequency, the more energy these packets carry. This limited the emission of energy at high frequencies, and the problem of infinite energy was solved. This quantum hypothesis was proven to be absolutely correct, but its implications for the deterministic universe were not understood until 1926. In 1926, Werner Heisenberg showed a fundamental limitation. If we want to measure the exact position and velocity of a particle simultaneously, a fundamental problem arises. To measure the position of an object, we need to shine light on it. But light is also a wave with a wavelength. If a short wavelength is used, the position can be found accurately. But the energy of the light will be high, which will disturb the particle and change its velocity. If a long wavelength is used, the velocity will be measured accurately, but the position will be uncertain. Heisenberg showed that the product of the uncertainty of position and velocity cannot be smaller than a certain number, which is called Planck's constant. This rule applies to every particle, regardless of the method used to measure it. This means that determinism has become impossible. If we cannot know the current state accurately, we cannot predict the future accurately. Heisenberg's uncertainty principle broke Laplace's idea of a deterministic universe. Now, the particles do not have a precise position and velocity. Rather, they have a quantum state that is a combination of both. Quantum mechanics does not give a single specific outcome, but rather a set of possible outcomes, each with a probability. If the same experiment is repeated over and over again, each outcome will occur a certain percentage of the time. Every correct outcome cannot be predicted in advance. Albert Einstein, who was himself a major contributor to quantum mechanics, could never accept this unexpectedness. He used to say that the universe cannot be run on randomness. He said that God does not play dice with the universe. But experiments have repeatedly shown that quantum mechanics is correct and randomness cannot be denied. Today, quantum mechanics is the basis of every modern technology, from computer transistors to electronics to chemistry to biology. But this theory has not yet been able to fit gravity and the large-scale universe together. Quantum mechanics has shown another strange feature: wave-particle duality. Light waves behave like particles. Particles behave like waves due to Heisenberg's principle. That is, both light and matter sometimes behave like particles and sometimes like waves depending on the situation. A famous experiment that proves this idea is the double-slit experiment. If there is a partition in front of a screen where two small holes are and light is sent from one side, then a pattern is created which we call interference fringes. This happens when light interferes in the form of waves. Now, if the same experiment is done with an electron, which is a solid particle, the same wave pattern is seen. That is, a single electron also goes through two holes together as if it were a wave. This is proof that things at the quantum level break the logic of our classical physics. This is where Bohr's atomic model and quantum mechanics come in. At first, people thought that atoms were like small solar systems. The electrons keep revolving around the nucleus, but according to classical physics, these electrons should lose energy and fall into the nucleus, and the atom should break apart. Niels Bohr came up with a solution in 1913. Electrons can only exist in certain quantum orbitals. But this explanation seemed arbitrary. Quantum mechanics explained it better. Electrons are not particles but waves. If an orbital is an integer multiple of the electron's wavelength, the waves will not interfere, and the orbitals will be stable. If not, the waves will interfere and cancel out. Quantum mechanics explains the microscopic world. General relativity describes the large-scale universe. But the two theories are incompatible. Where gravity is very strong, such as in black holes or the Big Bang, quantum effects cannot be ignored. Without quantum mechanics, general relativity predicts that the density of black holes and the Big Bang will become infinite, which makes no sense physically. This means that a complete theory will only be available when we can combine gravity and quantum mechanics into a theory of everything. In the following chapters, we will see how scientists are working towards this ultimate goal. Elementary particles and the forces of nature. Aristotle believed that the entire universe was made up of four basic elements: earth, air, fire, and the earth was made of matter and water. The two fundamental forces were gravity and light. Gravity pulls earth and water down. Light lifts air and fire up. This concept of matter and energy is still used in science today. But in modern physics, we know that this division is imperfect. Aristotle believed that matter is indivisible. A part can be divided into infinitely small parts. But Greek philosophers like Democritus said that matter is not indivisible. That is, it can be divided into small indivisible units, which they called atoms. In 1803, John Dalton supported the atomic theory. He showed that chemical compounds always combine in certain proportions. This is possible only when matter is organized into small indivisible units. But the final proof was found in the 20th century when Einstein explained Brownian motion. The random motion of particles suspended in a liquid was actually the result of collisions of atoms. This experiment finally showed that Democritus and Dalton were right. Matter is discrete. Until the beginning of the 20th century, people believed that the atom was the smallest elementary particle. But in 1911, Ernest Rutherford showed that there is a very small nucleus in the middle of the atom, surrounded by electrons. Research showed that the nucleus is also made of smaller particles. For example, protons and neutrons. This means that the atom was not indivisible, but there were smaller elementary particles inside it. Now the question was what particles matter is made of. In 1925, Wolfgang Pauli gave an important rule that two particles of the same type cannot be in the same state. This means that two particles with the same speed and position cannot be in the same place. This is Pauli's exclusion principle. Very important. If this rule did not exist, the electrons would fall into the same place and the atoms would break. Protons and neutrons would not be created. The entire universe would have become a dense soup. In 1928, Paul Dirac gave an equation combining quantum mechanics and relativity. He showed that the electron should have an anti-electron called a positron. In 1932, Carl Anderson discovered the positron and Dirac's theory was proven. Today we know that every particle has an antimatter counterpart. If a particle and its antimatter collide, both annihilate in a flash of energy. If the entire world were made of antimatter, we and an anti-world could exist separately. But the question is, why is antimatter so rare in the universe? According to quantum mechanics, all energy occurs through the exchange of small particles. Matter particles, i.e. electrons and quarks, feel energy. Energy-carrying particles, i.e. bosons, transmit energy. An electron or quark emits an energy particle and is consequently repelled. The energy-carrying particle reaches another matter particle. It is absorbed there and pushes or attracts the other particle. These energy-carrying particles are virtual. That is, they cannot be detected directly, but their effects can be seen. There are four fundamental forces in modern physics. One is gravity. It is the weakest but most important force. It acts everywhere, no matter how much mass there is. Gravity is always attractive. That is why planets and stars are formed together. It is the weakest force, but its spread is infinite. According to quantum mechanics, it is carried by a hypothetical particle called graviton. Two are electromagnetic force. That is a combination of electricity and magnetism. It acts on electrons and photons. Photons carry this energy. It is 1042 times stronger than gravity. Without it, atoms do not form and light does not exist. 3. The weak nuclear force is responsible for radioactivity. It acts on electrons and quarks. It is the cause of radioactivity such as beta decay. U+, W- and Z bosons carry this energy. In 1979, Abdus Salam and Steven Weinberg unified the electromagnetic and weak nuclear forces, which is called the electroweak theory. 4th, the strong nuclear force, which is the glue of the universe. It holds protons and neutrons together to form atomic nuclei. It interacts with quarks and gluons. It is the strongest, but its amplitude is small. The strong force has two strange properties. First, confinement, and second, asymptotic freedom. Confinement means that a quark cannot exist alone. It has to combine with another quark. That is how protons and neutrons are formed. Second, asymptotic freedom means that at high energies, quarks behave like free particles. Physicists are searching for a single theory of everything that can explain all forces in one equation. Electroweak theory has unified the electromagnetic and weak nuclear forces. There is also an attempt to unify the strong nuclear force, which is called the grand unified theory. But gravity has not yet been able to fit into any unification. A correct theory of everything will be found only when quantum mechanics and general relativity work together. Grand unified theory and matter-antimatter incompatibility. After the successful unification of the electromagnetic and weak nuclear forces, physicists took another big step, which was to try to unify the strong nuclear force as well. It was named the Grand Unified Theory, but this title is a bit of an exaggeration. This theory still cannot explain gravity. It has some parameters which has to be set experimentally. The theory itself does not make predictions, but it is an important step towards the theory of everything. The main idea of the Grand Unification Theory is that at high energies, the strong nucleon force starts to weaken. Conversely, the electromagnetic and weak nucleon forces start to strengthen. At a certain high energy point, called the Grand Unification Energy, these three forces become one. That is, the forces that appear to be different today may be different versions of one force. The exact value of the Grand Unification Energy is not known. However, it is estimated that it should be at least 15 to 10^16 Joule. Current particle accelerators can only reach 100 to 1000 GI. If an accelerator were built that could produce this much energy, its size would be equal to the entire solar system. Such an experiment does not seem feasible in the current economic situation, but we can test the low energy effects that Gut predicts. The Grand Unification Theory predicts something very strange. That is, protons can decay. Protons are the fundamental unit of ordinary matter. They can spontaneously decay into lighter particles. The quarks inside a proton can sometimes pick up extra energy. That is, due to quantum fluctuations. When this happens, the proton can decay into an anti-electron and other particles. But this decay is very slow. The probability of a proton decaying is so small that the lifetime of a proton can be as small as 10-30 years. That is, a proton can take 1,000 times longer than the Big Bang to decay. How can this be tested? By observing many protons so that occasional decays can be suspected. An experiment was conducted at the Morton Salt Mine in Ohio, in which 8,000 tons of water were used to reduce cosmic ray interference. But no experiment has yet detected proton decay. This means that even if protons decay, their lifetimes could be more than 1031 years. The simplest model of the cut has failed, but more complex models remain to be tested. The biggest unsolved mystery of the universe is where the antimatter went. At the time of the Big Bang, matter and antimatter should have existed in equal amounts. But today, antimatter is almost absent. If matter and antimatter were equal, both would have disappeared. The entire universe would be just energy, that is, light, and there would be no galaxies, stars, or planets. But we see only matter in the universe. So the question is, where did the antimatter go? According to the rules of quantum mechanics, an antimatter universe would behave exactly like our universe. Symmetry means that particles and antiparticles should be the same. But in 1956, a surprising discovery was made. The weak nuclear force breaks reflection symmetry. In 1957, Li and Yang confirmed that the weak force does not follow left-right symmetry. Then in 1964, another surprising discovery was made. The weak force breaks the antimatter symmetry. J.W. Cronin and Val Feach discovered this CP violation. They won the Nobel Prize in 1980. That is, the weak force does not see particles and antiparticles in the same way. This asymmetry may be one reason that the universe is made of matter, not antimatter. Another major symmetry is time reversal symmetry, that is, the T-symmetry. This means that if time is reversed, the laws of physics will remain the same. If a ball falls down, the opposite time will go up, but the rules will remain the same. But according to the CP theorem, if the CP symmetry is broken, then the time symmetry will also be broken, and experiments have shown that the weak force breaks the time reversal symmetry. That is, the universe is expanding, and the reverse is not possible. The time reversal version of the weak force does not seem possible. It proves that time flows in an irreversible direction. So the conclusion is that the grand unified theory does not unify gravity. But gravity is very important because the large-scale universe is governed by it. Stars collapse to form galaxies and black holes come into existence because of gravity. In the 1970s, Stephen Hawking worked on black holes. He took the first steps in unifying quantum mechanics and relativity. It was a trick of how a new model of quantum gravity could be created. In the following chapters, we will explore the deep mysteries of quantum gravity and space-time. We will see how black holes are not just traps, but dynamic systems that also interact with the universe. Black holes and their black form. Before 1917, Stephen Hawking's work had focused mainly on proving the Big Bang singularity. But when his daughter Lucy was born in November 1970, he began to think about black holes. His disability made lying in bed strangely the best time for him to think. At that time, there was no clear mathematical formula for defining a black hole. Hawking discussed with Roger Penrose that a black hole should be associated with events from which no light or matter could escape. The boundary of a black hole is the event horizon. It defines the path of photons that cannot escape. In a way, it is the edge of a shadow, a tinge of darkness. Then Hawking said something strange. The light rays of the event horizon cannot approach each other. Otherwise, they will meet, and if they meet, then it means they have gone inside the black hole. But if they go inside the black hole, then they cannot stay within the boundary of the event horizon. This means the event horizon of the black hole will either stay the same size or grow and never get smaller. This was a very important discovery. If new matter falls into a black hole or two black holes merge, then the event horizon of the final black hole will always grow bigger than before. Hawking saw that the size of the event horizon behaves like another thing, which is entropy. Entropy is a measure of disorder. The more entropy, the more disorder there will be. According to the second law of thermodynamics, entropy always increases. For example, if a room is left, it will gradually become more and more disordered. Hawking saw that the area of the black hole always increases, just like entropy. Jacob Bekenstein, a Princeton student, proposed that the event horizon of a black hole could be a measure of entropy. If entropy were to flow into the black hole, the area of the event horizon would increase. This would prevent the second law of thermodynamics from being violated. But Bekenstein had a problem. If a black hole had entropy and if something had a temperature, it would radiate. But black holes don't evaporate anything. So how could the concept of entropy apply to black holes? Hawking didn't believe this. He wrote a paper trying to prove that entropy and black hole radiation were problematic. But Bekenstein was ultimately proven right, in a way that no one had thought possible. During a trip to Moscow in 1973, Hawking met two Russian scientists, Yakub Zeldovich and Alexander Starobinsky. They said that according to quantum mechanics, rotating black holes should emit particles. Hawking thought this was physically correct but didn't like the mathematical proof. He started to solve the problem himself. He expected that only rotating black holes would emit particles. But when he did his own calculations, he got a surprising result. Not only rotating, but also absolutely stationary black holes emit radiation, and this radiation is like the radiation of a hot object. It follows exactly the emission rate that is needed to prevent entropy violation. That means black holes are not completely black. They emit radiation gradually. According to quantum mechanics, vacuum is not actually empty. It also undergoes small quantum fluctuations. Sometimes a particle-antiparticle pair is created. Usually they annihilate each other. But if it happens right on the edge of a black hole, a strange thing happens. A particle can fall into a black hole while another particle can escape. If the particle that falls in has negative energy, the mass of the black hole gradually decreases. And the particle that escapes becomes a real particle, which, when viewed from a distance, appears to have been emitted from the black hole. This radiation is called Hawking radiation. One interesting consequence of Hawking radiation is that black holes are not immortal. The smaller the black hole, the faster it will evaporate. The larger it is, the slower it will emit radiation. But as the black hole continues to lose mass, its temperature will continue to increase. There will come a time when it will become so hot that it will release all its energy in a final explosion. This explosion can be as powerful as 1,000,000 hydrogen bombs. This was a huge change in thinking. Previously, people thought that black holes were just traps where whatever fell in never came back. But now it is known that black holes themselves gradually evaporate. If Hawking radiation is correct, then this means that eventually all black holes will evaporate one day. This was the first real connection between quantum mechanics and relativity. If black holes evaporate, then another big question arises. Where does all the information that falls into a black hole go? Does it end there, or can it somehow come back? This is the question of the information paradox, which has not yet been solved. If a black hole is several times the mass of the Sun, its temperature will be more than 1/1,000,000th of absolute zero. This temperature is much lower than the temperature of the cosmic microwave background radiation, which is 2.7 degrees Celsius above absolute zero. This means that this black hole will absorb more than it emits. If the universe continues to expand, then one day the temperature of cosmic radiation will become lower than the temperature of the black hole. Then the black hole will slowly evaporate. But this process will take so much time that it is difficult to imagine. 66 years to the power of 10. This is the current age of the universe. 10 to the power of 10 is a few thousand times greater than 10 years. This means that the large black holes that exist today will not evaporate at all. If the small irregularities in the early universe had become black holes, their mass would have been about 1,000,000,000 tons. They would have evaporated by now. If a primordial black hole were 1,000,000,000 kilometers away from us, the distance to Pluto, its temperature would be about 300 billion degrees Kelvin. This means that even if it is a small black hole, it is smaller than a nucleus. Even if it were small, it would emit radiation like a hot white object. If it were any smaller, it would have completely evaporated by now. Such a primordial black hole would emit X-rays and gamma rays. These black holes were not black but white hot. They would emit up to 1,000 megawatts of energy per second. Such a black hole could power 10 nuclear power plants. A primordial black hole would weigh several billion tons. But it is as small as the nucleus of an atom. If it were on Earth, it would immediately fall underground. It would swing to the center of the Earth until it settled in the center. If it were to be used, it would have to be placed in an orbit in space. It would have to be somehow twined and taken into orbit, like dangling a carrot in front of a donkey. This is an unrealistic idea for now. If primordial black holes existed today, we would be able to detect them by their gamma rays. We would see a uniform gamma ray background. If primordial black holes had formed in such a way that we could see their radiation, they would now be a fraction of the total energy density of the universe. But there is no indication that primordial black holes are so abundant that they could produce 1% of the total energy in the universe. If primordial black holes were 1,000,000 times more common, the nearest black hole would be about the distance to Pluto, 1,000,000,000 kilometers, but their radiation would be difficult to detect from that distance. We would need a very large gamma ray detector in space. If such a black hole were to explode at the end of its life at a distance like Pluto, they would be easy to see. But if they were emitting tons to the power for 10 years, they are unlikely to explode in the next few years. That means they are difficult to detect directly. Satellites were launched during the Cold War to detect violations of the Nuclear Test Ban Treaty. They found that there were 16 gamma ray bursts per month in space. They were evenly distributed across the sky. This meant that they were either in our galaxy or somewhere else. If they were outside our galaxy, they would have been much more energetic than a tiny black hole. If they were in our galaxy, they would have exploded. Some scientists believe that they could actually be primordial black holes. But another explanation is that they are the result of neutron star collisions. New gravitational wave detectors such as LIGO could solve this mystery in the future. If we don't find a primordial black hole, it means that the early universe was very smooth and uniform. If it was irregular, then many more primordial black holes would have formed. If they didn't form, it means that the initial conditions were very stable. So the lack of black holes is also an opening. When Hawking first proposed that radiation could be emitted from black holes, not everyone was convinced. When Hawking showed his calculations at the Oxford conference, people were incredulous. The chairman of the session, John G. Teller, said it was complete nonsense. He even wrote a paper against Hawking. But eventually Teller and other physicists agreed that if quantum mechanics and general relativity were correct, then black holes must emit radiation. If a cosmologist were to fall into a black hole, his mass would be added to the black hole, but that mass would slowly return to the universe because of Hawking radiation. In a way, the cosmologist would be recycled, but his consciousness and memory would be lost forever. That would be a jobless immortality. Only the mass would return, not the person. There would come a point in time when the black hole would become so small that it would completely evaporate in a final explosion. When the mass of a black hole is less than a gram, Hawking's calculations may fail. Maybe the black hole will simply disappear. And if the singularity also disappears, it means that quantum mechanics has solved the infinity of relativity. Hawking began to develop a new method of quantum gravity. He used Richard Feynman's sum over history's method. If quantum gravity is a solid theory, it can give us a new model of the origin of the universe and the future. We will discuss this in the next chapter. How to understand quantum physics and gravity together. The origin of the universe and its consequences. According to Einstein's general relativity, space-time began with a Big Bang singularity and will end either in a big grand singularity, when the whole universe contracts again, or in an infinite expansion. When a local region, such as a star, contracts, it will create a black hole. If matter falls into a black hole, it is destroyed in a singularity, and its gravitational force can only be felt from the outside. With quantum effects, it is possible that the black hole will slowly give off its energy to the universe and eventually evaporate. A crunch could have the same effect. Does the universe have a beginning and an end? If so, what would it look like? Hawking expressed his interest in the origin and fate of the universe at a conference at the Vatican in 1981. The Church has been wrong about science before, like with Galileo. At the end of the conference, the Pope said that it was okay to study the universe after the Big Bang, but not to search for the cause of the Big Bang because it was the moment of creation that was only God's work. Hawking was happy that the Pope did not know that his speech was about that very thing. Hawking had a revolutionary idea. If space-time is finite but has no limit, then it means that the universe had no definite beginning. Right after the Big Bang, the temperature of the universe was very high. As the universe expanded, the temperature kept decreasing. When the universe doubled in size, the temperature was halved. As the particles cooled, they began to attract each other. At very high temperatures, particle-antiparticle pairs were created by collisions. But as the temperature continued to decrease, the annihilation of particle-antiparticle pairs became more frequent. If we go back, there was a time when the universe had zero size and its temperature was infinite. After 1 second, the temperature dropped to 10 billion degrees. The universe was then filled with photons, electrons, neutrinos, and their antiparticles. As the universe cooled further, electrons and positrons continued to annihilate, but neutrinos and antineutrinos survived. If neutrinos had had a small mass, they could have been a part of dark matter that could have compressed the universe again. After 100 seconds, the temperature dropped to 1 billion degrees. Protons and neutrons could no longer escape the nuclear force. Hydrogen atoms, i.e. deuterium and helium nuclei, began to form. 25% of matter was converted to helium. These nucleosynthesis reactions were predicted in 1948 by George Gamow and Ralph Alpha. They said that these ancient reactions should still be present in the universe today in the form of cosmic radiation. Penzias and Wilson saw this in 1965. The cosmic microwave background radiation was a major piece of evidence that the Big Bang model was correct. After 1 million years, the universe wasn't doing much. It was just expanding. One of its biggest advantages was that inflationary expansion meant that light could travel between different regions of the early universe. It also meant that regions that were quite far apart could still produce similar properties. This explains why the temperature is the same in every direction of the universe. It also solves another major problem. After the Big Bang, the expansion of the universe was very close to a critical rate. If this inflationary expansion hadn't happened, then a very carefully tuned initial state would have been required to understand this. Then where did all these particles come from in the universe? We can see that there are about 10 to the power 7 particles in the universe. According to quantum physics, energy can be made into pairs of particles and antiparticles. But where did the energy come from? Hawking said that the total energy of the universe is zero. The particles of matter in the universe are made up of positive energy, but this matter attracts each other, which creates a negative gravitational force. The two cancel each other out, resulting in the total energy being zero. That is, particles can be created freely in the universe without any external force, like an accountant writing zero on a balance sheet and then writing equal numbers on both sides. Goethe made an interesting point about this. The universe is the ultimate free lunch. Today, the universe is not in inflationary expansion. That means that some process has been used to reverse the expansion. During inflation, there was a high-energy state where the energies were in an equilibrium. As this equilibrium was broken, excess energy was released, which heated the universe again. Then the universe followed the normal Big Bang expansion, where it gradually cooled. Now we had an explanation for why the expansion of the universe was so close to the critical rate, and also why the temperatures were so similar in different regions. Goethe's original inflation model worked like a phase change. Just as cold water suddenly freezes, inflation would end with a sudden change. But there was a big problem that this phase change would occur in small bubbles. But the expansion of the universe was so fast that the bubbles were moving away from each other. They were not merging. If inflation had been like this, today's universe would not be uniform in one place but in different phases. Andre Linde raised this problem during a conference in Moscow. He said that if there had been a single big bubble during inflation that contained our entire observable universe, then this problem could have been solved. But then another problem came up. This bubble would have to be bigger than the universe. Hawking proposed a new model for the universe that instead of bubbles, symmetry breaking occurred everywhere at once. This meant that a Moser universe would have formed at the end of inflation. This solved the problem of how regions became uniform. Linde's model went in a new direction, and the new inflationary model was born. Another team, Paul Steinherr and Andreas Albrecht, both at the University of Pennsylvania, independently proposed a similar model. Together, these three are credited with the new inflationary model. The old inflationary model had fast symmetry breaking, but the new inflationary model had slow symmetry breaking. But this inflation, the ARI model, was not perfect either. Hawking and other scientists showed that the fluctuations in the microwave background that this model predicted were much larger than they actually were. And doubts arose about whether such phase changes could actually occur in quantum field theory. Hawking said that these models were once scientific theories, but were now dead because they did not match new data. Linde proposed another new model called chaotic inflation. In this model, there is no phase change. There is a quantum field that drives inflation. Due to quantum fluctuations, the field holds more energy in some regions, which causes inflation. When inflation ends, that energy is converted to heat, and the Big Bang expansion continues normally. This model had the advantage of all inflationary models without any incomplete assumptions. This model predicts a realistic size of fluctuations that match observations of the microwave background. So the most widely accepted form of the inflationary model today is chaotic inflation. One of the great advantages of inflationary theory was that it no longer required a precise tuning of the initial state of the universe. Inflation could have come from many different initial states to a single final state. This meant that the weak anthropic principle could be used to explain why the universe looks so well organized today. If inflationary theory were to be viewed backwards, then a well-organized universe did not emerge from every initial state. If there had been a lumpy and irregular universe, it would have remained that way even after inflation. So the initial state also plays a role. Inflation alone is not enough. Hawking also said that if the inflationary model is not a perfect theory, then should we accept the anthropic principle? Was it all just random chance? If we were to rely solely on lucky events, it would be a kind of defeat for science. To predict the conditions at the beginning of the universe, we need a formula that works at the beginning of time. If only general relativity were correct, there would be a singularity where everything would break down, according to the Penrose-Hawking theorem. But if quantum mechanics were included, perhaps the singularity could be avoided. We need a quantum theory of gravity that can explain this. The classical theory of gravity has two possibilities. Either the universe has always existed until the infinite past, or it began at a singularity, that is, a finite time. But quantum gravity shows a third possibility, that from the Euclidean concept of space-time, time becomes another space-like dimension. In this, space-time can be finite without any singularity or limit. Let's understand with an example. The surface of the Earth is finite, but there is no edge. If you set sail, you will not fall from anywhere. You can only return there. If space-time were like that, it would have no beginning or end. Just a self-contained entity that exists. If Euclidean space-time were extended to imaginary time, then singularities could be avoided according to quantum theory. Then there would be no need for a new formula or God for the beginning of space-time. No special boundary conditions would have to be defined. Hawking first proposed this idea at the Vatican. but its observations and implications were difficult to understand at the time. Later, the theory was refined further in Cambridge with Jim Hartle. Hawking and Hartle showed another important aspect of the no-boundary proposal. If we use quantum sum over histories, we can see which possible universes are more likely. This led to the discovery of a space-time model that behaves like a sphere. In this model, the universe starts at a point at the North Pole. As it progresses in imaginary time, the universe expands to a maximum size, i.e., the equator. Then it contracts again towards the South Pole. But here too, there is no singularity. Just like there are no sharp edges on the surface of the Earth, the laws of physics work everywhere, without any singularity. If viewed in real time, it would look like a Big Bang where the universe expanded. After a while, there might be another big crunch. That is, real-time singularities would be visible. But at the quantum level, they disappear. Hawking said an interesting thing. He said that perhaps the imaginary time we understand is the real time, and what we think of as real time is just a concept that we have created to understand it. Sum over histories considers different possible states of the universe. Each history involves a complete space-time and the people, galaxies, and planets that inhabit it. The anthropic principle can explain why we are in a history where life is possible. If the no-boundary condition is correct, we would expect the expansion of the universe to be the same in every direction and to be very likely. This is exactly what we see in observations of the microwave background radiation. Experiments by the Cobb satellite in 1992 confirmed that the universe behaves exactly as predicted by the inflationary model, the rise of small densities. The result was exactly what was expected due to quantum uncertainty. It was a strong demonstration that the no-boundary proposition could be a valid scientific theory. So what is the role of God? If the universe is self-contained, with no boundaries or edges, then this idea has generated a great deal of philosophical and religious debate. If the universe is self-contained, with no boundaries or edges, then what else is needed for God? In classical cosmology, if the universe came from a fixed beginning, then someone started it. That is, the idea of a creator logically fits. But if the no-boundary condition is true, then the universe never began. It has always been there, and no one has done anything to start it. Hawking said an iconic line about this. If the universe were self-contained, having no boundaries or edges, it could neither be created nor destroyed. That is, if the universe is self-contained, without any boundaries or boundaries, then it was neither created nor destroyed. Hawking does not directly deny any religious position. His point is that if science shows a self-contained model that explains the universe, then there is no need for supernatural intervention, but at the quantum level they disappear. Hawking said an interesting thing. He said that perhaps the imaginary time we understand is the real time, and what we think of as real time is just a concept that we have created to understand it. Sum over histories considers different possible states of the universe. Each history involves a complete space-time and the people, galaxies, and planets that inhabit it. The anthropic principle can explain why we are in a history where life is possible. If the no-boundary condition is correct, we would expect the expansion of the universe to be the same in every direction and to be very likely. This is exactly what we see in observations of the microwave background radiation. Experiments by the Cobb satellite in 1992 confirmed that the universe behaves exactly as predicted by the inflationary model, the rise of small densities. The result was exactly what was expected due to quantum uncertainty. It was a strong demonstration that the no-boundary proposition could be a valid scientific theory. So what is the role of God? If the universe is self-contained with no boundaries or edges, then this idea has generated a great deal of philosophical and religious debate. If the universe is self-contained, with no boundaries or edges, then what else is needed for God? In classical cosmology, if the universe came from a fixed beginning, then someone started it. That is, the idea of a creator logically fits. But if the no-boundary condition is true, then the universe never began. It has always been there, and no one has done anything to start it. Hawking said an iconic line about this. If the universe were self-contained, having no boundaries or edges, it could neither be created nor destroyed. That is, if the universe is self-contained, without any boundaries or boundaries, then it was neither created nor destroyed. Hawking does not directly deny any religious position. His point is that if science shows a self-contained model that explains the universe, then there is no need for supernatural intervention. But there is another philosophical thought, that if the no-boundary condition is the correct explanation, Yet who created these laws of quantum gravity that are so precise? Could this also be part of a divine command? This debate continues to this day in both science and philosophy. Is the universe the result of randomness or an intelligently designed system? If there is no creator, the question remains why the laws of the universe are so precise that we humans can exist. Hawking gives only a scientific view in his book. It does not prove that God does not exist, but it does suggest that he may not be needed. Hawking once said that science is answering questions that were once the preserve of religion. It was a pretty revolutionary idea that the universe had no absolute beginning, just a self-contained reality that exists. Before the arrow of time, people believed in absolute time. Each hour could be identified by a unique time number. All clocks showed the same time, but the theory of relativity said that each observer had their own time. Clocks of people moving at different speeds would not match each other. Then came quantum gravity. That's where the idea of imaginary time came in. Imaginary time is like space. You can go forward or backward. But in real time, the past and future look different. We can remember the past, but not the future. In real life, the past and future don't look the same. Time seems to move in one direction. We call this the arrow of time. There are 3 types of arrows. One is the thermodynamic arrow, which increases disorder or entropy. 2 are psychological arrows. That is, we can only remember the past, not the future. 3 cosmological arrows. That is, the universe is expanding, not contracting. Hawking said that the no-boundary proposal and the weak entropy principle explain why these 3 arrows point in the same direction. The second law of thermodynamics says that entropy or disorder always increases. Let's give an example. A cup can fall off a table and break. But after breaking, it does not fit back together. If you play a film in reverse, you will understand that this is unusual. This means that there is a specific direction in time for the increase in entropy, and it always increases forward. The direct meaning of increasing entropy is that the universe is going from a higher order state to a lower order state. If entropy could be reduced, then the cup could be thrown again. But this does not happen in the real world. This means that the universe started from a certain initial state, from a higher order state. Why can't we create memories in the future? Why can't we know the results of tomorrow's stock market? The answer lies in the brain and computer memory. Memory is stored in an orderly state. But this process consumes energy and increases disorder or entropy. We can only create memories in the direction where disorder increases. And we can only remember the past. A computer is not an example of memory. If an abacus is turned to the left or to the right, then energy is needed to define its state. If there is energy, entropy increases. We can only store memories in the direction of increasing entropy. And we can only remember the past. Another question is, why entropy and the expansion of the universe are in the same direction? If we look at the classical theory of relativity, we cannot predict how the universe began. It is not certain whether the universe came from a highly ordered state or was already chaotic. But according to quantum gravity and the no-boundary proposal, the universe began in a smooth and orderly state. Quantum fluctuations created some kind of anomaly that caused galaxies and stars. This explains why the arrow of entropy and the expansion of the universe point in the same direction. If the universe were to contract, would entropy reverse? Hawking initially believed that entropy could reverse, but he later admitted that this was wrong. Entropy would always increase whether the universe was contracting or not. Could entropy reverse if the universe ever started to contract? Or could time be reversed if someone were to become black? Will he see the universe moving? Will he make money today by seeing tomorrow's stock market results? Hawking said that's just science fiction. An astronaut falling into a black hole will not see the reversal of entropy. His arrow of time will remain the same as it was during the expansion of the universe. If the universe is expanding, then entropy is increasing. As long as the universe is expanding, intelligent life can exist. If it is contracting, then there will be no strong arrow of entropy. This is why we live in an expanding universe, because intelligent life could not exist in a contracting universe. That is, we are in a state where entropy and the expansion of the universe are both increasing in the same direction. The laws of science treat time forward and backward the same way. But there are 3 arrows of time. The thermodynamic arrow, which moves disorder. The psychological arrow, which means we can remember the past, not the future. And the cosmological arrow, that is, the universe is expanding. Because of the increase in entropy, we see time in a certain direction. We can only create memories in the direction where the chaos is increasing. The expansion of the universe and entropy are in the same direction. That is why we can exist. Even if the universe contracts, the entropy will not reverse. Time will remain the same. Hawking said an interesting thing, that if you have read and remembered this entire chapter, the order of your brain has increased by 2 million units. But you have spent so much energy that the chaos of the universe has increased by 10 million times. This is a simple example of entropy. As knowledge increases, the chaos of the universe also increases. The arrow of time will always move forward. And we can only live in this direction. Wormholes and time travel. Is time travel possible? In the previous chapter, we saw that time seems like a straight railway line where we can only go in one direction. But what if this line had loops or branches? Could we travel to the past or the future? Science fiction novels like H.G. Wells' The Time Machine have explored this idea. But just as submarines and trips to the moon were once just science fiction, could time travel one day become a scientific reality? For the first time in 1949, Kurt Gödel found a new space-time model of general relativity that allowed for time travel. Gödel's space-time model showed the entire universe in a rotating frame. If the universe rotated, a person could fly in a rocket and return before his journey. Einstein did not understand this, because he never thought that general relativity could allow time travel. But Gödel's solution does not apply to our universe. After Hubble's proof of the expansion, the cosmological constant was taken to be zero. Observations showed that the universe cannot rotate, so it remains a hypothetical model of time travel. But other space-time structures have been found that theoretically allow time travel, such as the interior of a black hole or two cosmic strings that are moving past each other at high speed. Cosmic strings are very thin and long objects that are held taut, weighing about a million tons. They can distort space-time in such a way that time loops can be created. But our observations show that the early universe did not have such a curvature that would support time travel. The no-boundary proposal also shows that the universe did not have such a structure from the beginning. According to the theory of relativity, nothing can travel faster than the speed of light. If we sent a spaceship to Alpha Centauri, it would take 8 years to return. If we went to the center of the Milky Way galaxy, it would take 100,000 years. But one big consolation is that according to the twin conundrum, an astronaut who went on a space trip would be younger than a person on Earth when he returned. But if he returns after thousands of years, his friends and family will be dead long ago. That's why science fiction writers use faster-than-light travel. But if we could travel faster than light, according to the theory of relativity, we could also go back in time. Relativity says that if an object wants to reach the speed of light, it needs infinite energy. Experiments in particle accelerators show that we can reach up to 99.9990% of the speed of light, but not more. If faster-than-light travel is not possible, then is there a shortcut? Einstein and Nathan Rosen came up with the idea of a wormhole, or Einstein-Rosen bridge, in 1935. A wormhole is like a thin tunnel that connects two different regions of space-time. If a wormhole were from the solar system to Alpha Centauri, a distance of 4 light-years could be covered in just a few million miles. But one big problem is that natural wormholes are not stable. They collapse quickly. If a civilization were to develop, they might be able to open a wormhole, but to distort space-time, negative energy density is required. Classical physics says that negative energy density cannot exist. But quantum mechanics says that quantum effects can allow negative energy density. The Casimir effect is experimental evidence that negative energy density exists. If we can one day create time travel, why haven't people from the future come to visit us? That there is a possibility. First, people from the future are hiding the secret of time travel from us. Second, the chronology protection conjecture, i.e. nature itself, prevents time travel. If the past can be changed, then an inconsistency will be created. If you kill your ancestors, you will not be born. If someone from the future comes and gives Nasser a nuclear bomb, how will history be changed? There can be two solutions. One is the balanced history method, i.e., if you go to the past, you will do what is written in history. You will not be able to change anything. If someone had time traveled to the past, we would have already seen its effects. Second, the alternative history conjecture, i.e., the multiverse theory. If you go to the past, you will be in a new alternative timeline. What you change will create a different history. Your origin will remain the same. The movie Back to the Future is based on this idea. In quantum mechanics, time travel occurs at a microscopic level. Particles and antiparticles can cancel each other out. Black holes can emit radiation due to quantum effects. But is it possible at the microscopic level? Hawking's chronology protection conjecture states that time travel would cause the energy density of space-time to increase so much that it would break down. This means that nature itself prevents time travel. Hawking said that if time travel were possible, someone from the future would come and challenge him. Wormholes and negative energy density could theoretically support time travel, but there are practical and logical inconsistencies. Maybe nature itself has made time travel impossible. The only option we have is to wait for the future. Unification of physics. Can everything in the universe be explained by one theory? In the first chapter, we saw that creating a fully unified theory is a very difficult task. Science has progressed by creating partial theories that explain various processes. For example, chemistry explains the molecular structure of atoms without understanding the internal structure of the nucleus. Physics has created different theories for different forces. A final theory should be one that can explain all forces and interactions of particles. It should not be fitted by introducing any unknown constants or numbers. This is the main goal of unification of physics. Albert Einstein tried to find a unified theory until the end of his life, but did not succeed. At that time, there was very little knowledge about quantum mechanics. Einstein did not believe in quantum mechanics. At that time, only two fundamental forces were known: gravity and electromagnetic force. But there was no knowledge about the strong and weak nuclear forces. Einstein's thinking was far ahead of his time, but the time was not right. Today we know more, and therefore the possibility of unification has increased. Earlier, people thought that science had reached its final knowledge. Max Born said in 1928 that physics would be finished within 6 months, because Dirac's electron equation had arrived. But when the neutron and nucleon forces were discovered, the whole model collapsed. Even today, we can get a possible grand unified theory, but we cannot be completely sure. So far, we have unified the three fundamental forces with quantum mechanics. The grand unified theory of the electromagnetic force, the strong nuclear force, and the weak nuclear force has been created. But the inclusion of gravity is not included in it. General relativity is a classical theory. Quantum mechanics follows the uncertainty principle. It is difficult to reconcile the two. When quantum effects were tried to be introduced into gravity, a big problem came to the fore: the infinite problem. Virtual particles are always being created and annihilated in the quantum vacuum. Their total energy is infinite. According to general relativity, this would create infinite mass, which would lead to infinite curvature of space-time. But we see space as a sphere in a sphere. It shows that quantum determinism and general relativity contradict each other. In 1976, a new idea came out: the theory of supergravity. It combined spin 2 with spin 3 by 2 and zero particles. It gave a unified framework that also included quantum effects. It had the idea of canceling out the negative and positive energies of virtual particles. But some of its mathematical calculations were very difficult. It would take 4 years to do a calculation. If you made a mistake, you had to start over. So no one had fully tested it. Even then, people thought that supergravity might be the right way to go. In 1984, the idea of string theory became popular. In supergravity, particles were like points. But in string theory, they are little strings. These strings create waves that we see as particles. Strings can also be added and broken. This also explains quantum gravity. But string theory brought with it new problems. It is only consistent when there are 10 or 26 dimensions in space-time. But we only see 4, 3 space and 1 time. One solution to this is that the remaining dimensions are very small, i.e., compactification. In 1994, a new idea strengthened string theory. Particles can be 0 brane, strings can be 1 brane, and there can be higher dimensional objects. Different string theories can be different approximations of a final theory. It says that there will not be a single theory, but many theories will come together to form a complete model. There are 3 possibilities. A complete unified theory is possible. One day we will have a theory that explains everything. 2. There will be an infinite series of theories. That is, new levels will continue to be found with new discoveries. 3. There will be no theory. That is, the universe is completely random and arbitrary. But quantum mechanics proves that randomness follows a certain rule. We cannot predict everything correctly, but randomness follows a certain rule. What would happen if a final theory were found? In Newton's time, a person could understand the whole of physics. Today, an expert can only understand a small area. If a unified theory is found, simplified physics will be taught up to the school level. But a big problem will arise that we will not be able to do theoretical calculations correctly. The mathematical complexity will only give approximate solutions. Will we know all the rules of the universe, or will new levels continue to emerge? What we know today is just the beginning. Conclusion: we live in a strange and diverse world. What is the nature of the universe? Where is our place in it? Who created it? And why did they create it? How was it created? Why was it created? Why is it this way? And why not something else? To answer these questions, we create a worldview. Just as in the old days, people thought that the Earth was placed on the back of a large turtle. Similarly, today we believe in models like superstring theory and quantum gravity, but no theory can be a scientific theory until it is proven. In ancient times, people believed that nature was controlled by gods. The sun, moon, mountains, rivers, everything was seen as a living being. To please these gods, offerings and sacrifices were made, but over time a strange thing happened. The sun rises every morning and sets every evening. Without any sacrifices or offerings, the moon and planets and stars continued to follow a certain path. Nature began to follow regular rules. This was the beginning of the idea that the universe followed a law. Until the 19th century, people began to think that there was a universal formula that could find the cause of every event. Laplace said that if we could know all the information about the universe at some point, we could tell its entire future. This was the idea of scientific determinism. This meant that everything was going to happen in a certain way, without any random events. But this theory had two major flaws. It did not say where these laws of the universe came from. Under what conditions did the universe begin? Laplace thought that this was something that God chose. God could have created the laws of the universe but would not have interfered in the middle. Quantum mechanics put an end to Laplace's determinism. According to the uncertainty principle, the velocity and position of a particle cannot be known precisely at the same time. Particles do not stay at a fixed point but behave like waves. Randomness is a fundamental property that prevents any theory from making 100% accurate predictions. Is this randomness God's intervention? It could be that we are misunderstanding the concept of particles and waves. This book focuses specifically on the laws of gravity, because gravity, although the weakest force, determines the large-scale structure of the universe. The laws of gravity say that the universe cannot be stable. It will either expand or contract. According to general relativity, there will come a time when the universe becomes infinitely denser, i.e., a singularity will form. A singularity is a point where all the laws of physics fail. When quantum mechanics and general relativity were combined, a new idea emerged that time and space could be a finite four-dimensional structure that exists without limits. Just as the surface of the Earth is a sphere, space-time could also be a four-dimensional structure. If the universe is completely self-contained, what role does God play in this? Einstein once asked how much freedom God had in creating the universe. If the no-boundary proposition is correct, then he had no freedom. There may be only one self-contained theory that allows creatures like humans to understand. A theory is just a set of equations. But the question arises as to why these equations describe the universe. Did they come into existence by chance? Or was there a creative force that drove them? And if there was a creator, who created him? These questions of why have not been explored in science as much as the questions of how. There was a time when philosophers worked in all areas of science and knowledge. Everyone from Aristotle to Kant wondered about the laws and beginnings of the universe. But as science became more profound and mathematical, philosophers fell back. In the 20th century, philosophers like Wittgenstein were limited to the analysis of language. But if we find a complete information, it will not be just a matter for a few scientists. All people, scientists, philosophers, and ordinary people, will think about it together. If we find the answer to the question of why we in the universe came into existence, then that will be the peak of human intelligence. The end will be triumphant. One day this knowledge will be available to everyone, not just scientists, but to every ordinary person. And then perhaps we will find the answers to the greatest mysteries of our existence.